Okay, welcome to my second video. Today we'll be starting a new chapter, which is stochastic, and this will be the theme for the next few videos. And today we'll be starting with combinatorics, so the science of counting variations in experiments, in random experiments. So why do we need combinatorics? Why do we need to count stuff? Let's say we have an experiment and we have a ball, and in this ball there's a yellow, a green, and a blue ball. And we're pulling them out and we don't put them in, back in. And now we have multiple variations. Our first variation, for example, is that we first draw yellow, then blue, then green. We could also draw yellow, then green, then blue. And if we draw blue in the first draw, then we have two other situations where we could either draw blue, yellow, green, or blue, green, yellow. And the same is with green. We can either pull green, yellow, blue, or green, blue, yellow. So this is really easy to just write down and count, like on paper. It's really easy. But what if we have 10 different balls? Then things become a little bit more challenging, as you need much more time and much more space for if you just want to write them on paper, and if you don't have a formula for them, it can get really tedious, especially in higher numbers, even beyond 10. What if you have 20 or 30 different balls? You're playing the lottery and you have 100 different balls. So this is why we need combinatorics for random experiments, so we know how many variations we have in the end. When we're talking about random experiments, we're talking about permutations and combinations. So this is where the order in which we draw matters or not. If you go back to our first experiment here, you'll see that the draw order does matter, because yellow, blue, green in the end is something different than blue, yellow, and green. Even though we drew the same balls at the end, the order is what matters here as well. And with combinations, we don't care about the order. It's just about what balls did we have in the end. And there's a formula for each of them. Also, if we care about repetition or not. For example, here we don't have any repetition since we don't put the balls back in. So we can only draw yellow one time. We can only draw blue one time. And we can only draw green one time. And yeah, for each different combination of these, there's a formula, and I will explain each and every formula. In this video, we will only talk about the permutations. We will only talk about where order does matter, and we will not talk about any combinations where order does not matter. They're a little bit more difficult, but we will cover them next video. So let's start with permutations with repetition. So we have three different balls. We have green, yellow, blue again, but we put them back in every single time. So for our first pull, so we can pull any amount of times, as much as we want, because we never run out of balls since we put them back in. And for our first pull, there are three different variations. We can either draw the green one, we can draw the yellow one, or we can draw the blue one. Pretty simple. And the problem now is, what if we, how many different solutions do we have if we pull for an arbitrary amount? So I call it R, because it's usually called R, the amounts of pulls you do. And this is now the question becomes, how many variations do we have if we, let's say, pull 5 different times? And we can easily get there if we just talk about what happens when we draw a second time. So here, for example, if we draw the green one, we put them back in. We can either draw a green one again, the blue, or the yellow one. So it's the exact same as here. And the same as when we pull the yellow ball. We can, after we pull the yellow ball, we can either pull out the green one, the blue one, or the yellow one. And after we draft or pull out the blue one, we can either pull out the green one, the blue one, or the yellow one. Since we put them back in, we can also draw them again, and the chances for them to appear again always stay the same. They're not getting lower, since there are only always 3 balls in the bowl, and we don't add any balls, we don't subtract any balls. So for the first bowl, we have 3 different pulls. Then for each of these pulls, we have 3 different pulls again. So we have 3 plus 3 plus 3, or 3 times 3 different pulls. How is that? Like I said, we draw out of the same bowl, the same balls every single time. So you can think of like our first pull to be like the set pull, our main pull that we always have. We can always pull the green, the yellow, or the blue one. And it does not matter what we pulled beforehand. We can always draw the green, the yellow, and the blue one with the same chances. So if you, for example, now, after the second pull them again, we can again either draw the green, the blue, or the yellow one. So here, after green, green, we can either pull green, blue, or yellow. After green, blue, we can either draw green, blue, or yellow. And after green, yellow, we can either draw the green one, the blue one, or the yellow one. So for all these 9 different solutions, or different different solutions for our problem, different sets, we can draw 3 more different sets after we draw again. So we have 9 times 3 different sets for 3 different, if we pull 3 times. Or we have 3 times 3 different pulls. Oh, here should stand r times. Sorry, I was yeah, there should be r times, not n times here. And for r pulls, it is 3 times 3 r times, or just 3 to the power of r. So the general formula is n times r. You can think of that, for example, if we have 4 different balls, we wouldn't talk about the green, yellow, blue ones, but the green, yellow, blue, and red one, and it will always be possible to either draw the green, the yellow, the blue, or the red one. So it's the same thing like with 3 balls, only with 4 balls, and then we have 4 times 4 r times, or 4 in the power of r, and this is then written as n to the power of r. So this is like the simpler thing. Now it gets a little bit more interesting. So we have this formula here explained. We know how to get to it, and now we want to get to this formula with order but no repetition. So how can we do that? Let's say we have a ball, and we have a ball, and in them we have 4 different balls in the number of 1 to 4. So there's a little number written on them. I think of like in a lottery or in a bingo game. And we pull them out and we don't put them back in. So once we have one number, we cannot pull the same number again. So after one pull, we have 1, 2, 3, 4 different solutions, different sets, because we can either draw the 1, we can either draw the 2, we can either draw the 3, or we can either draw the 4. Now after we draw the 1, we cannot draw the 1 again, so we can either draw the 2, the 3, or the 4. So it cannot appear again. The same with the 2, cannot appear again. We either have the 1, the 3, or the 4. And with 3, we also have 3 different sets, and for the 4 as well. So for each different pull at the first pull, we have 3 different pulls for our second pull. So we have 4 times 3 different pulls after we pull 2 times, or 4 times 3 different sets. And now after we draw the 1 and the 2, we can only draw the 3 and the 4. And after we draw the 1 and the 3, for example, we could only draw the 2 and the 4, and so on. So for each of these 4 times 3 or 12 different sets, we have 2 times the amounts of sets again. So we have 4 times 3 times 2 different sets after 3 different pulls. And now when we pull out all the balls, we already know what ball we pull out at the fourth pole. It's always the one remaining. So here, if in this example, for example, when we first pull out the 1, then the 2, then the 3, we already know we have to pull out the 4. So it can already stop here. So there won't be like more added, because we already know if you have the 1, the 2, and the 4, there will be a 3 here. There will only be one number available here, only one ball available here. That's the 4 in this example. And here we only have the 2 available, here only the 3, and here only the 2. So we already know what ball we're pulling out after we pull out 3 times. So we have 4 times 3 times 2 times 1 different outcomes. And this here is where we have a number and we take it times the lesser number, then again one less, the number 1 less, and then again the 1 less until we hit the 1. It's called factorial. So 4 times 3 times 2 times 1 is written as 4 factorial. It's just to save some time. For example, if you have like 8 factorial, it's really easy. It's really hard to just write them out, or it takes time to write them out. It takes space to write them out. So we just notate it as 4 factorial with an exclamation mark at the end of it. So, but now we don't pull out all the numbers, we only pull out 2 numbers. So now we stop after r equals 2. So what happens now? So you can kind of just disregard this whole section here. We only have the 4, and then after the 4 different solution sets for one different pull, and then the 4 times 3 different sets for the next pull. So we only have 4 times 3. And you can already see that from the 4 factorial, there's this little 2 times 1 is missing. So our new formula is something like 4 factorial, 4 times 3 times 2 times 1, over 4 minus 2. Why 4 minus 2 factorial? Because 4 minus 2 factorial is 2, and 2 factorial is 2 times 1. This is what we talked about earlier here. 4 factorial is 4 times 3 times 2 times 1. 3 factorial will be 3 times 2 times 1. And 2 times 2 factorial is 2 times 1. So we know that our new formula is now 4 factorial over 4 minus 2 factorial, because we can disregard the 2 poles, the 2 next poles. And if we, for example, pull only 1 time, then we know that from 4 times 3 times 2 times 1, there is the 3 times 2 times 1 missing. So it would be 4 factorial over 4 minus 1 factorial, because that would be 3. 4 minus 1 is 3. And 3 factorial is 3 times 2 times 1, and it's what's missing here if you only have 4. And if you pull 3 times, then only the 1 is missing, and then we have 4 minus 3. So you can already see the r in here. But what about the n? Why is the 4 in here 2 times? You can think of it, what if we have 5 different poles? Now we can draw 5 ones at the first pole, and then 4 at the second pole, 3 at the third, 2 at the fourth, and only 1 at the fifth pole. So we have 5 times 4 times 3 times 2 times 1, so that's 5 factorial. So here we have the 5 factorial again. So the n factorial, we know that this one. And now if we only pull 2 times, then we know that we have from the 5 times 4 times 3 times 2 times 1, we only calculate 5 times 4. So 3 times 2 times 1 is missing, and that would be 4 minus 2. Here again, r is our 2. And here again, we have then n minus r. So n is the number of balls we have, r is the number of poles we do. And then we have the general formula here. And that this will also line up with what we are giving, what formula we're giving. It's n factorial over n minus r factorial. And this is the solution for if we care about the order, but we don't have any repetition. And this one is not only used in bingo, but also in like a race you can think of. You can think of it instead of the different balls you pull out as different people who are racing. So we know that when 4 people are racing, um, like the first one, if like number one, the first person is the first one to finish this race, so like they all have different numbers, like running numbers, from 1 to 4. And if the number one is first, then they cannot be number two or number like the second or the third one. Um, and if you only care about the first two um, people that finish the race, or the first 3 people that finish the race, then it's the exact same with where we have r equals 2 or r equals 3. So we only care about the first 2 or the first 3 people to finish this race. So this is like another example of a permutation without repetition. So yeah, thank you for listening. I hope you learned something, and I will see you in the next Combinatorics video where I will explain the other two formulas. Yeah, thank you for listening.